All right, welcome everyone. Let's get started. So today we're going to finish off talking about indeterminate forms. So we're going to look at indeterminate differences and indeterminate powers. And then once we finish with that, we're going to move into our next major unit and really look at a lot of the definitions that we're going to be talking about for the next few weeks. All right, so let's just finish up talking about indeterminate forms and L'Hopital's rule, and then we'll get started on that next unit. So this is where we left off. We left off with indeterminate differences, and these happen when we're computing the limit of a function f of x minus another function g of x. And what happens is the first function there is going to infinity, and the second function is also going to infinity. And so we have a large term minus another large term. So what makes this indeterminate? Well, if our first function wins, if f of x wins, then the overall result will go to infinity. The overall difference there, f of x minus g of x, the whole thing would just go to infinity. Our second function could win. So g of x could win, and in that case, it would make the whole result would want to go to minus infinity. Now there's another possibility, is that the two functions sort of balance out. And that's another option, in which case our limit would go somewhere in between, some number in between. So it's indeterminate because we don't know what happens. We have to investigate it a little bit further. It's a mystery. And our strategy for doing this is that we try to rewrite the difference as a quotient so that we can go on and use L'Hopital's rule. Or, and we've seen this strategy before, we try to rewrite the difference as a product. So let's just see what that might look like. Say we had the limit of x squared minus x as x goes to infinity. That's an example of an indeterminate difference. Why? Well, because that first part of the function wants to go to infinity. We're subtracting, and then the second part of that function x also wants to go to infinity. And so there's sort of like this conflict here. The first term wants to get really large. The second term wants to get really large, but we're subtracting. So the question is, which term wins out? So this is an indeterminate difference. So we can't just say, what it is. We have to do a little bit more work. And what we did before, it still works here, is that we could just rewrite this as try to factor. So we try to factor and we rewrite it as a product. So x times x minus 1. And with that, we can say, well, we have a large positive number times another large positive number. And so the result is large positive. So if we take a large positive number, multiply it with a large positive number, the result is some other large positive number. So this limit is infinite, goes to infinity. So this is just an example of what you might do if you wanted to rewrite as a product. Try to factor. That's really the key step here, is you try to factor it. We're going to see an example, though, where we try to rewrite it as a quotient. So we'll see how to do that in the next example. But just going back to the definition here, there's similar definitions for the left-hand and right-hand limits, and then also the limits at infinity, where x goes to infinity and x goes to minus infinity. So there's similar definitions for this indeterminate form. All right. Let's try an example, and we're going to see how to rewrite a difference as a quotient. And we're going to look at the limit as x goes to 1 from the right of the function 1 over natural log x minus 1 over x minus 1. So first, kind of what we've been doing, the first thing we want to check is this actually an indeterminate form? So let's just check that out. So let's look at 1 over natural log x as x goes to 1 from the right. And I'll leave it for you to kind of fill in the details here, but this limit is positive infinity, and then the limit of the other term, 1 over x minus 1 as x goes to 1 from the right, is also positive infinity. And you could check both of those by identifying them as a c over 0 form and then using test numbers. So we did that way back. One of the first things we talked about in the course was these infinite limits where we had a c over 0 form. So we would identify that it's a c over 0 form. That was our first step. And then we would use a test number to decide is it plus or minus infinity. So I'll leave it for you to fill in a little bit of the details there on why each of those limits individually is infinity. But putting them together, we get that this is an infinity minus infinity form. So it's indeterminate. And so what we're going to do is we're going to get a common denominator so that we can combine those fractions into one quotient. So let's see what this looks like. So let's write our first fraction. It had natural log x in the denominator. Now the quickest way to get a common denominator is just to take the two denominators that you have and multiply them together. So we'll take the natural log x and we'll multiply it with x minus 1. Now for that first fraction, we can't just put something in the denominator. We have to balance it out and put the exact same thing in the numerator. So we're going to put an x minus 1 up there. Then we're subtracting. And then in that second fraction, the original denominator was x minus 1. But again, to get the common denominator, we would need to multiply that by ln x. And we can't just put something into the denominator without also putting it into the numerator as well. So we're going to put a natural log x in the numerator there. And that's our first step. Just trying to get a common denominator. Now when we have a common denominator, we have two fractions, we can combine them into one fraction. So we end up with x minus 1 minus natural log x all over natural log x times x minus 1. So basically, we just subtract the numerators there. So we have x minus 1 in the first numerator minus natural log x from the second numerator. And this gives us a brand new kind of function to check. So let's just see what happens. So we're going to check this. So let's plug in x equals 1. So when we do that, we get 1 minus 1 minus natural log 1 over natural log 1 times 1 minus 1. And natural log 1 is equal to 0. And 1 minus 1 is 0, so we see that this is a 0 over 0 form. So also indeterminate, so that's not the answer, but it does give us a little bit of information. It tells us that we can actually use L'Hopital's rule. So let's apply the rule. So we're going to apply a little h there. We're applying L'Hopital's rule. We indicate that in our work. So we differentiate the top function. So derivative of x minus 1 is just 1. Derivative of natural log x is 1 over x. So our numerator, once we differentiate, becomes 1 minus 1 over x. And then for the denominator, there's a little bit of work there. We need to use the product rule. So it's natural log x times x minus 1. So I won't go through all the steps for product rule, but we would end up with 1 over x times x minus 1 plus natural log x. So we had to use product rule here. All right, so we applied the L'Hopital's rule. Let's just check to see if that gives us anything. So we're just going to check again. We're going to plug in x equals 1, see what we get. And if we get a number, good, then we're done. But let's check it. So we get 1 minus 1 over 1. 1 over 1 times 1 minus 1 plus natural log 1. And in the top there, we get 1 minus 1, which is 0. And then in the denominator, natural log 1 is also 0. So we end up with a 0 down there as well. So still no good. It's indeterminate, 0 over 0 form. So that tells us we're not done yet, but it does give us an idea of what to do next. It tells us we can use L'Hopital's rule again. Now, before we actually do that, let's try to simplify our function down a little bit, our expression down a little bit. And what we're going to do is we're going to get rid of some of the other fractions. Let's just multiply the top and the bottom by x. So we can do that because it's just a fancy one that we're multiplying by. But that's just going to help us get rid of those 1 over x terms so we don't have so many fractions floating around. So let's see what happens when we do that. So if I distribute the x into the numerator, I'm going to end up with x minus 1. And then if I distribute that x into the denominator, I'm going to put it on the natural log x, and then I'm going to put it onto that first term. And so when I multiply it into the denominator there, I get x minus 1 plus x times natural log x. So we've simplified it down a little bit. Now let's actually apply L'Hopital's rule. So let's differentiate the function in the top. Derivative of x minus 1 is just 1. And then the derivative of x minus 1 in the bottom is also 1. And then there is another product here. There's this x times natural log x. So we'd have to use product rule for that as well. So if we use the product rule, we'd end up with I'm not going to show all the little steps there, but we'd end up with x times 1 over x plus natural log x. And then we try plugging in again just to see what happens. And if we do plug in x equals 1, we get 1 over 2 plus natural log 1, which is 1/2. So we get a number. That's our answer. It's not indeterminate now. So that tells us that is the value of this limit. All right, so for this one, kind of a few things here. We had a indeterminate difference, so we were subtracting, and we had to rewrite it as a quotient by getting a common denominator. And then we actually had to, once we had the quotient, we had to go through and use L'Hopital's rule twice. All right. Let's just talk about the indeterminate powers. Now, these don't show up too much, but they show up enough where we'll kind of briefly talk about it here. So this is where we're looking at the limit of some function f of x raised to some other function g of x. So we have a base term and we have an exponent that both have variables in it. So there's a few different possibilities. We could have where the base term goes to 0 and the exponent term goes to 0. So we call that the 0 to the power 0 form. And so what happens when the base term is going to 0? When our base goes to 0, it wants to make that whole expression. It wants everything to go to 0. So it wants that whole function f of x raised to the g of x. It wants that whole thing to go to 0. Now when our exponent is going to 0, it wants something different. So if our exponent is going to 0, we know when we normally raise things to the 0 power, it wants to make it 1. So with our exponent going to 0, that kind of wants to turn that expression and wants to force it and make it closer and closer to the number 1. So the base term and the exponent want two different things. The base term wants to make the whole expression go to 0. The exponent makes it want to go to 1. So does the base term win? Does the exponent win? Or do they balance out and we get something in between? So that's the mystery. We don't know what happens. Same thing if we have the base term going to infinity. So if the base term goes to infinity, it wants the whole expression then to go to infinity as well. But there's a conflict. The exponent term is going to 0. And so we know when the exponent wants to go to 0, it wants to force the whole thing down to 1. So our base term wants the whole expression to go to 0 or go to infinity. The exponent wants the whole expression to go to 1. And so they want two different things. So the question is, does the base term win? Does the exponent win? Or do they balance and we get something in between? Again, it's a mystery. We don't know what happens. And then the last indeterminate power is the type 1 raised to the infinity. So our base term is getting closer to 1. Our exponent is getting large positive or negative. And what happens is if the base term is going to 1, it wants that whole expression then to go to 1 as well. But if our exponent is getting large, the exponent then wants the whole expression to get very large as well. So again, there's a conflict there. Does the base term win and we go down to 1? Does the exponent win and we get really large? And I should say, possibility there, if g of x is approaching minus infinity, then the possibility is that we also go to 0 as well. So there's again a conflict. The base term wants the whole expression to go to 1. The exponent term wants everything to go to either infinity or 0. And so there's a conflict there. And another option is they might just balance out. So we don't know what happens. And as usual, there's a similar definition for left-hand and right-hand limits and limits at infinity. Now one that's not on this list, 0 to the infinity, is not indeterminate. So there's no mystery there. So if our base term is going to 0 and the exponent is going to infinity, it might look like it's going to be indeterminate, but it's not. It's actually just the whole limit would go to 0. So that one's not indeterminate. but the three other ones are. And how we handle these, we've looked at functions like this in the past, where we had f of x in the base and then some other function in the exponent. So we have x terms in the base and x terms in the exponent. And the way we would handle those in terms of differentiation is with logarithmic differentiation. And so that's going to be sort of our strategy for how to calculate this limit. It's going to feel very similar to a lot of the steps that we did with logarithmic differentiation. So let's look at an example. We're going to look at the limit as x goes to 0 from the right of x raised to the square root x. Let's just check that this is an indeterminate form. So the base term is going to 0, and then our exponent, which is square root x, is also going to 0. So our base term is going to 0, our exponent is going to 0, so we end up with a 0 over 0 form, or 0 to the power 0 form. So how we're going to handle this is very similar to the steps that we used for logarithmic differentiation up until the last step. So let's start, call it step 0. We're just going to write down our function, and we'll call it y, just to give it a name. Then in step 1, we're going to apply natural log to both sides. So we get natural log y on the left, we get natural log x raised to the power square root x on the right. Then in step 2, we're going to simplify the right-hand side. So this is where we use our log rules. So we can bring that exponent, that square root x, we can take that square root and put it in front of the natural log. So we get square root x times natural log x. So we've simplified the right-hand side as much as we can using our log properties. Then in step 3, so far that all should feel very similar to what we would do with logarithmic differentiation. Now we're not actually differentiating here, we want to do the limit, so that's where it starts to kind of deviate here. We're going to do the limit of both sides now. So we're going to apply the limit to the left-hand side as x approaches 0 from the right. And then we're going to apply the limit as x goes to 0 from the right to the right-hand side of our equation. So all we did was just apply the limit sign there to both sides of our previous equation. And this limit that we have here, we already calculated this in a previous example. So last time. So that was example 6. And we saw that the limit was 0. So there normally would be a lot more work here. So that's an indeterminate product. We'd have to write the product as a quotient, then use L'Hopital's rule. We did all that in a previous example. So this is going to look short, but it's really not. There was a whole bunch of work here to show that this limit is equal to 0. So that's where L'Hopital's rule comes in. And that's where the main portion of your work is going to be. Then once you actually have that limit, then we just want to kind of convert back. So we're just going to use a property that y is equal to e raised to the natural log of y. And again, that's because e and natural log cancel. So that's going to allow us just to convert back. So up until this point, we have, at the end of step 3, we have the limit of natural log y. we didn't want the limit of natural log y. We want the limit of just y. So how do we convert back? Well, this is the limit that we want. We renamed that x raised to the square root x. We just called it y. So equivalently, we could just find the limit of y as x goes to 0 from the right. Now we use that property that y is equal to e raised to the natural log of y. So that's all we're using there, is just y is equal to e raised to the natural log y. And that's because e and natural log are just inverse functions, so they would just cancel out. And then e is the exponential function is continuous, so we can bring the limit up into the exponent there. So e is continuous. So we can bring the limit inside of a continuous function. And then the limit of natural log y is something we just did in step 3, so we can just fill that in. So we get e raised to the 0, and e raised to the 0 is just 1. So this is the kind of the steps for how to handle these indeterminate powers. It starts off feeling pretty similar to logarithmic differentiation, and then step 3 is really where the new L'Hopital's rule might come into play. And then step 4 is just converting back to the original expression. All right, so just a few other indeterminate forms there. So that'll do it for our discussion of indeterminate forms. And now we're going to move into kind of the next major unit. And we're going to be talking about, well, it's going to be a lot of definitions. So we're going to introduce the concepts of increasing, decreasing, concave up, concave down, and local maxes and local mins and absolute maxes and absolute mins. And we're going to see a little bit on how these relate to our derivatives. So our original function f, f prime, and f double prime. So we'll kind of develop an intuitive idea of what it means for a function to be increasing, decreasing, concave up, concave down, and how it relates to all of our derivatives. And then for the remainder of this unit, we're going to kind of explore these definitions and how to calculate these more precisely. So we're going to be talking a lot about this topic over the next couple weeks. So we're kind of introducing all the definitions in this first section. All right, so let's start off talking about what it means for a function to be increasing and decreasing. So there's a few ways to characterize an increasing or a decreasing function. And primarily what we're going to be looking at today is graphically. So that's what we're seeing here in the first part of this definition. This is really the graphical idea of what it means to be a function to be increasing. So a function's increasing on an interval if the graph of that function rises as x goes from left to right throughout that interval. Now we could also define increasing based on inequalities, and this is the more technical approach. So this looks like it's an if-then statement. So if x1 is less than x2, then our function is increasing provided f of x1 is less than f of x2. So an increasing function preserves the inequality. So if we have two numbers, one is bigger than the other, well then when we plug them into our function, it keeps the same inequality. Now for a function to be decreasing on an interval, the graphical definition is that the graph continuously falls as we go from left to right throughout that interval. So this is the graphical definition. Now the technical definition is again with inequalities, and we see that if x1 is less than x2, then the function, if it's a decreasing function, reverses the inequality. So if x1 is less than x2, then f of x1 is greater than f of x2. So these inequalities, this is how we precisely define increasing and decreasing. As it turns out, it's very difficult, or it's difficult to prove that a function is increasing, decreasing just using those inequalities. And what makes it difficult is the definition only has two x values there. If we're talking about increasing on an interval, there's normally a whole bunch of x values that we need to check. So we'll see how later on we'll see how to check increasing, decreasing, exactly. Right now we're just trying to develop just an intuitive idea of what it means for a function to be increasing or decreasing on an interval. So we're primarily going to stick to the graphical interpretation. So graphical, an increasing function has an upward trend. Simple as that. We graph it, the graph goes up. Now it might go up kind of like a line, but there might be some bend to it. So maybe it bends like this. Could bend like that. Still moving up as we go from left to right. Or it might do so a little more subtly, and it might look like something like that. But all those three examples there, each one is moving up as we go from left to right. Now decreasing, maybe I'll give these some different colors. Decreasing is following a downward trend. So maybe it looks something like that, looks sort of linear. But it might have some bend to it, some curve to it. So maybe it looks something like that. Still decreasing. It's going down as we go from left to right, or maybe something like this. So again, moving as we move from left to right, the graph is falling down. So really that's the interpretation we're going to be looking at just right now. Just graphical. So let's just look at an example, well, a few examples. So we're going to determine if the following graphs are increasing, decreasing, or neither at x equals c. So let's start with the first graph there on the left. And see that it's increasing at x equals c. So why is it increasing? Well, a few reasons. So first, the graph is rising. It's going up near x equals c. So right around that point, the graph is moving up as we go from left to right. But another interpretation is if we were to draw the tangent line at that point. Let's draw in what we think the tangent line looks like. We see that the tangent line has a positive slope. So there's a few ways to kind of characterize the increasing nature of this function at x equals c. The graph is moving up right around x equals c. It's rising. If we were to draw the tangent line in, we'd see the tangent line is going up. It has a positive slope directly at x equals c. So all of these mean the same thing. Now, what about that graph all the way to the right? At x equals c, at that point on the graph, here we see an example of a function that is decreasing at x equals c. So as we move from left to right, what happens is the graph is it's going down, it's falling. So the graph is falling near x equals c. But if we were to think of it in terms of tangent lines, let's draw in what we think the tangent line looks like. And let's use red. Maybe something like that. Again, that's our tangent line. And we see that the tangent line is going down. So it has a negative slope. Just another way to characterize the fact that our function is decreasing at x equals c. Right around x equals c, the graph is falling, it's moving downward. But the tangent line, if we draw on the tangent line, the tangent line has a downward slope as well, has a negative slope. Now directly at x equals c, or in the middle example here, we see that it's neither. It's not increasing, it's not decreasing. And what's happening to our graph is the graph is flat at x equals c. So if we were to think of that in terms of our tangent line, let's draw in our tangent line. The graph is flat. If we draw in our tangent line, it's a flat tangent line, has a slope of 0. So what we're seeing here is when our function is increasing, the tangent line has a positive slope. When our function is decreasing, the tangent line has a negative slope. And then when our function sort of flattens out, the tangent line has 0 slope. So these are kind of the three little examples to keep in mind of the different types of possible behavior for our function in terms of increasing and decreasing. All right, so kind of related to increasing, decreasing, and we'll see why it's related, is the idea of the extreme values of our function. So first definition, we're going to define what it means to be a relative max or a relative min. We also call it a local max or local min. So, I'll probably use those just interchangeably. So we say that a local maximum value of our function f, well, it's a number f of c such that f of c is greater than or equal to all of the other function values f of x for x near c. And then a local minimum is just a value of our function, so f of c, such that f of c is less than or equal to all of the other function values f of x for x near c. So let's kind of look at the first graph here. This is an example of a local maximum at x equals c. And we can see that right around x equals c, that's a high point. That's a high point of our graph. So that's a local maximum. It's a high point of our graph. All of the other function values around that are slightly lower. Or they could be the same, but in this case they're slightly lower. And what we're noticing here, if we look to the left of x equals c, on this side, our graph is increasing. And then on the other side, our graph is decreasing. It's moving down. And so another way to characterize a local maximum is when we have this switch from increasing to decreasing. Let me write that up here. So when we see that behavior in our graph, when we go from increasing on one side to decreasing on the other, we have a local maximum at that point in the middle. Now in the other graph here, this is an example of a local minimum. So we have a local minimum in this case at x equals c. And again, let's see what happens to the left. So to the left, we have decreasing, and to the right, our graph is increasing. So on the left there, the graph is going down, and then on the right, it's going up. And so another way to characterize a local minimum, it's a low point on our graph. So right around x equals c here, that point is as low as we can go. So that's a local minimum. But another way to characterize it is when we have that switch from decreasing to increasing, we get a local minimum in that case. So if we see this behavior where our graph switches from decreasing to increasing, we have a local minimum. And just to mention it, for a lot of our discussion here, we're going to be assuming that f is continuous. You can kind of cook up some crazier examples where there's breaks and jumps in your graph, and so some of these characterizations don't work if your function's not continuous. For right now, we're talking about continuous functions. All right, so that's the definition of local max and local min. Local max is a high point on our graph, local min is a low point. And just one thing to kind of emphasize here, f of c is the min or max value. So when we say the local maximum value of our function, we're actually talking about the function value f of c. And then a lot of times we then say which occurs at x equals c. So sort of x is the location where the max or the min occurs, and then y, the function value, is the actual minimum or maximum value of our function. So it's just kind of a thing to remember. F of c is the actual value of our function, and then the max or the min occurs at x equals c. All right, so that's local min, local max. So we're just kind of going through some definitions here, and we'll look at some examples dealing with these definitions as we go. So related to local max and local min, well, we could talk about the absolute maximum or the absolute minimum. We also use the phrase global max and global min. So you might see those as well. You might hear me say global max or global min. And so the definition for absolute max, well, we say that the absolute value, maximum value of our function f, it's a number f of c such that f of c is greater than or equal to f of x for all x in the domain of f. So if we go back just for a second to local max, very similar setup to our definition. It's a value of our function such that f of c is greater than or equal to f of x. The difference here is that local max was for x near c. Absolute max is just for all x in the domain of our function. So if we were to trace out the whole graph of our function, the absolute max is the absolute highest point on our graph for the entire graph. So kind of think of it when we're talking about absolute max and local max, think of it like mountain peaks. So every mountain peak is a local maximum, but Mount Everest is the absolute maximum. So this is the largest value over our entire domain. And the absolute minimum, very similar setup. It's the smallest value over our entire domain. So it's the absolute lowest point that our graph ever gets. All right, so just a few comments here. These can occur at local mins or maxes. Or at endpoints. So if our graph has any endpoints, it might happen there as well. So there's a few different places where we might have an absolute max or an absolute min. They might happen at a local max, or they might happen or a local min, or they might happen at an endpoint on our graph. Another option is that a function does not necessarily have to have an absolute max or an absolute min. So it might have one and not the other, might have neither of them, or it might have both. So just a few observations there. So an absolute max or an absolute min could occur at a local max or local min, or might happen at one of our endpoints. And a function's not guaranteed to have an absolute max or an absolute min, though. So let's just look at a few examples. So let's start with that graph on the left. Here we see a graph that has two endpoints. So it has an endpoint over here and an endpoint over here. And then it has a few local mins and, well, it has one local min and one local max. So here we have a local max. And then over here we have a local min. Write that up here. So we have a local max point, we have a local min point, and then we have a few endpoints on our graph. Now, what is the absolute max value of our function? Well, the absolute max is the absolute highest point on our graph. And we see that it happens at x equals -1. So the absolute max is the y value. So the max value is equal to 5. And this occurs at x equals -1. So the highest point on our graph here, the value is 5, sort of like the elevation. So if we're thinking in terms of mountain peaks, you know, what is the highest mountain? Well, it's Mount Everest. So what is the elevation of the peak? And then the x-coordinate is just where it happens. Then absolute min, let's look on our graph. This is the absolute lowest point on our graph. So we see that it happens at x equals 3. and the value there is 1. So our absolute min value, the lowest we ever go, is 1. And this occurs at x equals 3. So that first graph on the left has both an absolute max and an absolute min. Now let's look at the one on the right there. Again, we see an endpoint. We see a local max over here. We see a local min. Very similar graph. We see a local min there. And we're just extending that left side now. It keeps going. So when there's no endpoint actually drawn, the way we read the graph is the graph just keeps going in that direction, forever. So if we were to try to determine what's the absolute max and the absolute min of this graph, well, what's the absolute max? It's the highest point on our graph. And we look, the contender is right here. It's this endpoint. That endpoint is included on our graph, and it's higher than any of the other points along the rest of our curve there. So that endpoint, that's where our absolute max occurs. And the value is 6, and it occurs at x equals 5. Now, if we were to try to find the absolute minimum, the contender would be that local min. One of the contenders, at least, would be that local minimum. But if we look over here, eventually the curve goes below that local minimum. So that's still a perfectly good local minimum, right in the neighborhood there, right around x equals 3. That is the lowest spot on our graph. But if we keep going, if we go further out, eventually we get lower than it. And that's what we're seeing on the left side over here. Eventually we get lower than that local min, and then the graph just keeps going down. So there actually is no absolute minimum for this function. So there's not a minimum, absolute minimum value for this function. But there is an absolute max. So you can cook up examples where, well, maybe there's an absolute min but not an absolute max, or maybe there's neither. All right, so we're moving along here. So it's just kind of going through definitions. So we're just introducing all of the terminology and gadgets that we're going to be looking at. So we've talked about increasing, decreasing, local min, local max, now absolute max, absolute min. And the last major definition, well, two of them, have to do with the changing behavior of our slope, which is really going to define the shape of our graph. So let's just, as a little prologue to this, let's look at two kind of examples here. On the one on the left, we have a graph of a curve. So here's our curve. And same thing on the right there, we have our curve. And then we've also drawn on a few tangent lines. So here's a tangent line. There's a tangent line. So we have two different curves and then a few different tangent lines drawn along each of those curves. Now let's start with the graph on the left. And if we look at this, let's start with the leftmost tangent line that we see here. And if we were to characterize this, this would have a small positive slope. It's kind of flat, but it is still going up. So it's positive, but it's not very impressive, so it's a smaller positive slope. Now let's look at the tangent line further to the right along that curve. Now there the tangent line is steeper. So this is going to have a large, and it's going up, so it's positive. So the tangent line there would have a large positive slope. And so what we see in this first example here, as we move from left to right, the slope is increasing. So on the left we start small and positive, and then on the right we get to large and positive. So it's an increasing slope as we read left to right. Now if we look at that graph, the other graph, if we start with the one on the left along the curve, the leftmost tangent line there, we see that the tangent line is kind of subtle, but it's pointing down. So it's going to be small and negative. So we have a small negative slope over there. Now if we were to move further to the right and look at that other tangent line, this is more dramatic. It's a steeper tangent line. So it's going to be large, and it's pointing downward, so it's going to be negative. So as we look at this curve, as we go from left to right, we start small negative, and then we become large negative. So in this case, the slope is decreasing as we read from left to right. So this idea of having our slope change, so the tangent lines are getting steeper, getting more positive, or the tangent lines are getting more negative, this idea of having our tangent lines kind of change is related to the next idea. And that's concavity. So we say that at x equals a, our function f of x is said to be concave up if the graph of f of x lies above the tangent line at x equals a, and we say the function is concave down if its graph lies below the tangent line at x equals a. So the key words here are above and below. So concavity really has to do with the shape of our graph. So increasing, decreasing just kind of gives us a rough idea of the overall behavior. Is the graph going up or down? But concavity adds some shape, tells us how the function is bending, as we'll see in a few examples. So what does a concave up graph look like? And I'll usually abbreviate this CU. So concave up looks like a U shape. Might look like the whole U shape, or it might look like just the left side of it, or it might look like just the right side of it. And what we see in each of these is if we were to read each of those graphs left to right, we would see that the slope of each is increasing left to right. So as we read each of those graphs left to right, the slope of our tangent lines would be increasing. So when our slope is changing, that tells us something about the concavity of our function. What does concave down look like? Well, concave down, I'll abbreviate that CD. And this kind of concave down like a frown. So you draw in the upside down U, the frowning shape there. So it might look like that whole thing, or it might look like just part of it. So it might look like the left side or just the right side. So that's generally, if our function has a concave down shape, it's going to be one of those three options. And if we were to read each of those graphs left to right, what we'd be seeing is that the slope of our tangent line is decreasing as we go from left to right. So just another way to characterize concave down is our slope is decreasing as we go from left to right. And let's, in an example, in a few of these, let's just draw in some tangent lines just to see how it relates to the idea of the graph lying above or below the tangent line. So if I were to pick any point along each of these curves, let's pick, we'll pick one right here, this concave up. If I were to draw in the tangent line at that point, I notice that the section of curve, my actual graph, is above the tangent line right around that point. Now, if I were to do something for the concave down shape, pick any point on those concave down shapes and draw in a tangent line. So maybe something like that. And I'd see right around that point of tangency, the graph is below the tangent line. So there's just a few ways to kind of think of concave up, concave down. Think of it where the graph is above or below the tangent line, or we could think of it in terms of changing slope. The slope is increasing or the slope is decreasing. So with that, just like there were local maxes and local mins when we were talking about increasing, decreasing, there's what we call inflection points when we talk about concavity. So we say that an inflection point, it's a point on the graph where the function is continuous and it changes from concave up to concave down, or the opposite, goes from concave down to concave up. So let's just look at a few examples here. In the curve there to the left, we see that in this section of our graph, we have a concave up shape. So it has that kind of U shape there. In this section over here, we have that frowning shape, that upside down U. So that's concave down. And then right there in the middle, that's our inflection point. So right where it switches from concave up to concave down, that's our inflection point. Now for that graph in the middle, the section on the left here is concave down, so it's part of that U shape, or upside down U shape. And then on the right, it's concave up. So it has that U shape over there. So just sections of the U and the upside down U shapes. And then right in the middle, where we switch from concave down to concave up, that's our inflection point. So it happens at a specific point. And then same thing for that graph on the right. This section over here has that concave down shape. And then over here, it has that concave up shape. And then right in the middle, right where it switches, that's our inflection point. And so when we talk about concavity and inflection points, again, we're talking about, for right now, we're talking about continuous functions. So that's just one requirement here for an inflection point, is we want our graph to be continuous there. So really no jumps or holes or breaks in our graph. All right, so let's kind of put it all together and let's look at this graph here and just identify the intervals where this function is increasing, decreasing, identify the intervals where this function is concave up, concave down, find any local maxes or local mins, same thing for absolute maxes and absolute mins, and inflection points. So we're just going to go through all those definitions that we found and just kind of see what's happening on this particular function. All right. So let's start with, what do we want to start with? Let's start with local max and local min. Those are kind of the easiest to identify here. So we see that, maybe not the easiest, but they tend to be where at least my eye gets drawn. So we see that we have a local maximum right here. So we have a local max at x equals 5. And then the local minimum is, or at x equals 3 rather. So the actual maximum value though is 5. So the local maximum value is equal to 5, but it occurs at x equals 3. Now, what about the local minimum? Might not have a local minimum, but we see a low point right here on our graph. So that occurs at x equals 5. And the value, the local minimum value there, we kind of have to estimate it. So, I might say 3.6. It's a little bit bigger than 3.5. So I'd say maybe 3.6. So that's our local max and local min, just high points and low points on our graph. Now what about absolute max and absolute min? Well, those local maxes and local mins are the contenders, but if we look at the end behavior here, towards the left here, it's cut off, and the way when we read a graph, the way we read that is it just keeps going in that direction. So what we're seeing here on the left is that eventually it's lower than the point at x equals 5. So on this left-hand side here, eventually our graph goes lower than our local minimum. And it just keeps going lower and lower and lower. So there is no actual absolute minimum here. And if we look at the right end behavior of our function, so if we look at the other side, it gets just kind of cut off. And the way we interpret the graph is that it just keeps going on in that direction forever. So it just keeps going up and up and up and up. So eventually, on the right side there, the right end behavior is higher than the point at x equals 3. So our local minimum was a possible contender for being the absolute maximum, but we see that this right end of our function eventually gets higher and just keeps getting higher and higher. So there is no absolute maximum for this graph. All right, let's look for the intervals, though, of increase and decrease. And we see that when we identified our local max and local min, those points really split up our graph. So those local maxes and local mins, they split up the behavior of our graph. So if we look to the left, our graph is increasing over here. And that's because, it's moving up. Same thing if we go all the way to the right, also increasing over here. So our graph is moving up. So we say that our graph is increasing on the intervals minus infinity to 3 and 5 to infinity. So we just, again, we interpret the graph that it just keeps going forever to the right and forever to the left. So that's why we're using minus infinity and infinity as our end values there for those intervals. And then right in the middle, we see that our graph is going down. So our graph is decreasing on that middle interval. So in between 3 and 5, the graph is decreasing. So on the interval from 3 to 5, our graph is decreasing. Now, concave up and concave down, we're just looking at the shape of our function here, the shape of our graph. And so concave down, we're looking for an upside down U shape. And we see that kind of right around this peak here. And then for concave up, we're looking for a U shape, and we're seeing it right along this low point over here. And so when we have a section of our graph that's concave down, another section that's concave up, there must be some point in the middle where it switches. And it looks to be, it's kind of hard to identify, but it looks to be right around that point there. And where we have that change in concavity, that's our inflection point. So to the left of x equals 4, our graph is concave down. To the right of x equals 4, our graph is concave up. And then directly at x equals 4, that's where we have our inflection point. So our inflection point occurs at x equals 4, and our concave up interval is from 4 to infinity, and our concave down interval is from minus infinity to 4. So all we've done so far is just looking at a graph, just being able to identify these different behaviors. Now it turns out, and this is really where we're going to be putting a lot of our attention, is these behaviors are related to the first and the second derivative. So we're going to first look at the first derivative rule. And what this says is that if our derivative is positive, then our function is increasing. So if our derivative is positive, then the original function f of x is increasing. And that's really what the first derivative rule tells us. So if f prime of a is greater than 0, that just means it's positive. Then f of x is increasing at x equals a. And then similarly, it says if f prime of a is less than 0, so if the derivative is negative, well then the function f of x is decreasing at x equals a. So f prime of x, if it's negative, then our function is decreasing. All right, and we've kind of seen this before, or we've kind of been talking about this a little bit. It's been hanging around the edges, and now we're kind of just formally stating it. So if f prime of a is greater than 0, the derivative is measuring the slope of the tangent line. So if f prime of a is greater than 0, the slope of the tangent line then is positive at x equals a. And so what that means is if we have a curve and we draw in our tangent line at a point at x equals a, if that tangent line is positive, it means it's going up, and that kind of means the whole curve is going up right at x equals a there. It's increasing. Same thing if f prime is negative. So if our derivative is negative, then the slope of the tangent line is negative. That's what the derivative means. The derivative is just giving us the slope of the tangent line. And so if we draw in a tangent line that has negative slope, it's moving downward, and that must mean then our graph must have a similar shape as well. Must be moving downward as well. So it's decreasing. All right, so next time, we'll stop there for today, but next time we'll see how to kind of use information about f prime to sketch the graph of a function f of x. So as we get going, there's a question, and I'm going to go back here. So going back to this example, when we look on a graph, really we're just estimating. So when we read off points and y values and x values, we are just estimating. So particularly probably noticeable right here where I said this was approximately 3.6. So when we read a graph, we all the values that we're reading, we're really just approximating. So we don't know exactly. Even the x values here, these all happened at grid lines, most of these. So maybe like this point here, maybe the graph, these are kind of thick lines. So maybe this is actually at x equals 5.001. So, when we read a graph, we're everything that we're reading off of it is in some way an estimate. We're going to see how to actually calculate these values exactly later on once we start working with the actual functions. Right now we're just kind of reading graphs, so everything that we're doing is an approximation. All right, so let's stop there. We'll continue on Tuesday. So this was really just a lot of introducing definitions and ideas that we're going to be talking about for the next couple weeks. And then one last reminder, next week is our recitation exam 4. So it will cover learning outcomes D5, D6, and then our application section DA1, DA2, and DA3. So it will cover indeterminate limits and L'Hopital's rule. I'm not going to put on the indeterminate differences or indeterminate powers, but it will cover indeterminate quotients and indeterminate products. So it will cover overall the exam, recitation exam 4 will cover five of our learning outcomes. D5, D6, DA1, DA2, and DA3. And I'll post a reminder of that on the course website as well. All right. So have a good weekend. Have a good rest of your day. And then we'll see everyone next week. And remember, I have office hours tomorrow. So if you do have any questions on last exam, the homework, feel free to stop by my office hours and ask. Or on the course website as well. All right. Have a good weekend. Bye-bye.